to calculating the EMF using Faraday's Law. The first part is generating or figuring out what the flux is. Bless you. And then the second part is figuring out how that flux changes, and that's dealing with taking the derivative. I'll put the N in there too. So if you look at the history of what we talked about, the first one we did is we changed the area specifically. We moved the wire loops into or out of the magnetic field. We started that conversation with motional EMF. We generated an expression for that, BLV. Some of you think that was the thing, but that's not it. That's only if you're trying to move the wire loop into or out of the magnetic field. And in all certainty, that will generate an EMF, but as we talked about, it generates other problems too. Like the fact that once the entire loop is inside your magnetic field, you're not generating anything anymore, because it's only while the actual area is changing relative to the loop. The next one we talked about was changing the magnetic field. So we specifically did something here. We did that two different ways. One was just some time rate of change of the magnetic field. Any expression for that is fine. Don't get hung up on the expression they might give you for the magnetic field. The expression can be anything. It can be linear, if they feel like it. That'd be the easiest, but I've seen quadratic on the exam. I've seen exponential. And I've seen exponential decay. So they can pick any function they want here. They can change the magnetic field in any way that they want. You're just taking the derivative of that time function. So there's been more than once, and you're going to see one later this week, where they've put a complicated function around the magnetic field. Something with a lot of constants in it. They define the constants as all just being some value based on a non-changing parameter of the equation, and it looks super complicated, and somewhere buried in there is a t. And all they're trying to get you to recognize is that you just take the derivative of that function regardless of what it is. It's not about the function. It's about the idea that the function is showing that the magnetic field is changing. So don't get hung up on whatever this is. It's not going to be a part of your summation. It will pass through the summation, because for any moment, all you need to worry about is whether the magnetic field is uniform in the space or whether the magnetic field is different from place to place. That's this part. What does the magnetic field look like in the space, frozen in a moment of time? Now, this is a dot product. So the only other possible thing that we would have left is to manipulate the dot product. And this means manipulate the orientation of the loop relative to the magnetic field. So there's not a whole lot to talk about with this one today, but that's the one we're going to talk about today, since it's the last one. Any one of those is a way of generating an EMF. By the way, this is probably one of the primary ways that we actually generate electricity. There's two different ways. There's rotating the magnet inside the loops, and there's rotating the loops inside a magnetic field. We do it one way or the other, but every turbine generator is operating on that principle. Something's rotating, something's spinning, either because you're passing steam through it. If you're burning fossil fuels and boiling water, you're putting it on the top of a pole and letting the wind blow it. You're using some kind of steam brought up from a hydroelectric plant, or you're allowing water from a dam to flow over it. You are spinning something. And generally, it's either a fixed magnet that's spinning inside a coil of wires, or it's going to be the coil itself spinning. And both of them produce most all the power that's here. We take whatever the frequency is of that particular loop, and then we try and transform it to match what we want to have in our outlets here at this school. All right. So I can't really draw this particularly easily, so I'm going to do my best, but it really doesn't matter what shape of wire I try to draw here, because we're going to place the entire wire inside, or the entire wire loop inside the region of the space that has the magnetic field. So all we ultimately care about is that we have some expression for the area of that wire. So whether it be a circular loop or a square loop, it doesn't matter. What you have to recognize is that we're going to place the entire loop inside the region of space with the magnetic field, so the entire area is exposed to that magnetic field. So don't be thrown off by the fact that on the test, they might have a square loop of side S or a round loop of radius R or diameter D. Don't be thrown off by that. As long as you know how to calculate the area of that shape, all they care about, and all you should care about, is having the area here. Because we're going to sum up over the entire area, assuming the magnetic field is a constant in that region of space. So let's start with just a square loop, a square-ish loop, perhaps. Maybe. So I'm trying to put it kind of sideways because our magnetic field will have passing through this loop. So I've tried to draw this in such a way that it has a clear look that the magnetic field is in line with our area. And for this argument, I'm just going to say that it has a total area of A. You calculate the area of your shape, but for us, let's just use a placeholder of A. Is that okay with all of you? Because it just doesn't matter what the shape is as long as you have the area. Now, the idea is that we're going to take and rotate the loop relative to the magnetic field. So we'll start off with this idea that the area, or a piece of the area, is currently aligned with our magnetic field. But there's going to be a future where our loop is not going to be aligned with the magnetic field. So what we've tried to do here is try to indicate that I have turned the loop relative to the magnetic field. So this angle is now the angle between my magnetic field and the direction of my area. Everybody okay so far? Now, what we're really going to be talking about is the fact that we're going to take and spin our loop. So the loop is rotating in this region of space. So theta is not constant, although I'm using two different symbols, so let's make sure I use a consistent symbol. Phi is not constant. Phi is changing with every moment in time because the whole loop is rotating at speed omega, where omega is in radians per second or something similar to that. Everybody good so far? So any questions about the parameters I've set up? All right. So calculate the flux first. And this is going to be super straightforward because there's not a whole lot to do. To calculate the flux, if the magnetic field is uniform in the region of space, even if the loop is kind of turned relative to the magnetic field, that part doesn't matter. All that matters is if the magnetic field is the same everywhere in that region of space. And if it is, the magnetic field gets pulled out of my integral. Next, I'll have dA here, but I have to add in our expression for the dot product, which is going to be cosine, in this case, phi. So to complete calculating the flux, I just sum up over the whole area. Now this gives us our expression for the flux. B and A aren't changing relative to the motion of the loop. They're staying the same. The only thing that's changing is phi. Phi is changing because the actual loop is rotating. So now we're going to pass this expression on to Faraday's law, where we're going to take the derivative. I dropped N because there's only the one loop. But of course, if they say there's 20 loops of wire, and I don't know if you guys have picked this up, but they don't have to say loops of wire. What's the other word they could use? Have you read through any of your homework? Turns. I don't know who said it, but that's the other word they'll use. So if they don't say loops, they'll say turns. Turns of wire means number of loops. Don't make that a big deal. All right. Lenz's law is a little complicated here, and I think we'll come back to Lenz's law in just a minute. So that's that negative sign. But I think we can probably recognize that B and A are going to pass through the derivative. They're not changing as time changes. So our derivative passes to the one thing that does change with respect to time, and that's the cosine. Now we have an expression, just a simple rotation. It's spinning at a constant rate relative to our motion. So we're going to sub that in for our phi. We'll put omega t in there. So that gives us B times A times the derivative with respect to time of cosine omega t. My understanding is that you guys are pretty good at doing this derivative. What is the derivative of cosine with respect to t? Sine, so it's got a negative sign, so that's going to cancel out our negative that we had there. But that negative is still all about Lenz's law. We get sine of omega t times omega, because we have to use the chain rule. It is definitely appropriate to consider the dynamics real briefly of this. And I think there's nothing big here. First, our EMF isn't constant. Do you see it's going to have some kind of sine function? This is what I mean when I say that almost all the way we generate power comes from this. This is the way Tesla thought that we should generate power, is by generating AC. He thought it was the reciprocal nature of it would make it easy to produce, and that the mechanics of it would make it easy to produce. There's also some other things we're going to learn about when it comes to transformers. That is a good reason why you would use AC power as opposed to DC power. It's really easy to change the peak voltages and the frequency using step-up and step-down transformers. And so we'll talk about transformers in a day or two, probably closer next week, because we have to get through something called mutual inductance first. But I do want to point out that the size of the EMF is dependent on how fast you spin the loop. That it creates a larger EMF, higher voltage, higher peak voltage if you spin the loop faster. So, because this whole thing is still just a sine wave, but this is the peak of that power. Now, there's a couple of problems with AC that might not be readily evident if you're not thinking it all the way through. Everything we've worked with so far this year has always been something that is constant. We've dealt with batteries, we've dealt with power supplies that are DC power supplies. AC power supplies are a little bit different in that you're never getting the same voltage all the time. In this one, we're looking at a sine function. But if this is our EMF as a function of time, you're going to get something that looks like this. There's just some stuff that doesn't work well here. Now, part of the reason we used AC early in our electrification of the United States was because the only thing we were lighting up were light bulbs. And at the time, they were Edison's light bulbs, which means they used a piece of tungsten in them. Although it doesn't care whether the current's going one way or the other. It generates light based on heat. So as long as you can run current through the filament and the filament gets hot, it's going to give off light. So it didn't matter that we were using some kind of AC power source, since all we were doing was turning lights on and off. Well, eventually we started making things like fridges, and we started making things like vacuum cleaners. Those were starting to replace what we had in the house. And so we couldn't just be arbitrary about the way we sent in AC power. So we started to change the way we put in power. We've fixated on a specific frequency. So you could make motors that were modularized to accept that frequency of AC current. Everything in your house now is designed to accept specific frequencies of AC current using transformers inside the product itself to distribute the energy in a way that the motors in those things, the compressor motor of a fridge, the oscillating, rotating motor of your washing machine, the way it can use that particular pulsation of power. However, all these things stop working almost right away, but the current's never constant. And because the current's never constant, you can't calculate power this way. You have to find a different way to try and determine how much power there is, because you're never at the peak. You're only at the peak for an instant. You spend half the time or the same amount of time at zero as you do at the peak. So the actual amount of power dissipated by one of these circuits isn't ever what we would normally calculate. So this kind of calculations of energy, all have to be adjusted. We generally use something called RMS. Has anybody heard this phrase before? It's a math phrase, and all of you mathletes should be perking up right now because this is your moment to show me how smart you are. Not a one of you. All the things you know. Come on, you're going to go compete and take a couple days off and go to Orlando. You can't tell me what RMS means. What's the average? And I'm going to ask the math kids who are not paying attention right now, what's the average over one cycle of this particular graph? Come on, smart kids. What's the average voltage? It's zero. That's right. So how do you find an average when the average is zero? Does it look like zero is happening here? So how would you kind of express what's really happening? One way to estimate it is called an RMS, root mean square. You do it in opposite order. You square the function first. That makes all of it positive. You then compute the average over the cycle, and then you take the square root. It's a way of calculating an average for something that has an average of zero. And it's used all the time in anything that's sinusoidal because it has an average of zero all the time. So one way to deal with that is called the RMS. RMS ends up being about 72% of the peak. So if you calculate an RMS on a sine function, you'll get about 72%. So that would suggest that the power on average would be 0.72 times BA omega. Be about the average power over one cycle, because that is what the RMS output would look like. Actual experimentation through the outlets is about 68%. So you actually never get the true RMS. RMS is an estimate of what we think the power output would be, but doesn't actually get close enough to the actual value. There's no easy way for us to do experiments like this to measure the amount of energy. I don't have the proper equipment for it. But RMS is a pretty good way of getting you kind of a quick and down and dirty average of what it is. And the 0.72 probably comes from something you can probably imagine here, something around the square root of 2. So it's going to be a factor in the way RMS is calculated. I just thought that this might be something you know about, since you guys do work in the area of functions, right? You learn about sine functions and cosine function in pre-calc, and then you do it again when you get to calculus. So RMS has never come up as a means of dealing with an average. It's too bad, the things they don't tell you. All right. So 3 different ways of calculating power. There's changing the magnetic field, changing the area exposed to the field, and rotating the loop in the field. Do you see pretty clearly that the direction of the current is going to be constantly changing? Is that pretty obvious? So do you also notice that in one loop we get actually 4 cycles? You should look closely at how that would work, because in every quarter turn, we're changing whether the area is getting bigger or smaller relative to the field. So in going from here to here, trying to figure out the direction of the current is a little challenging because it's I'm drawing it on a 2-dimensional board and it's a 3-dimensional loop. But is the area getting bigger or smaller? So the area is getting smaller. So what we're going to try and do is generate a current that's going to try and preserve the flux. So that's going to be a current that complements the magnetic field that's dying. So our loop is going to try and produce a magnetic field that is this way to reinforce what's being lost. But that'll only work until we get to 90 degrees. At 90 degrees, suddenly the magnetic field disappears relative to the area. And then on the other side of that, we start growing an area. So the direction of the magnetic field is going to be to try and oppose the magnetic field that's being impinged on our loop. You follow me? So that'll work until we get back to, say, this. And then it starts all over again. Because our magnetic field is constant and always pointing in the same direction, the direction that we call the positive area is also going to be upwards the whole time. Because once the loop flips over once, it starts over again. It doesn't start with an opposite flux. It just starts over again once we flip over once. It's not particularly hard. You're not going to be asked those questions because they're not going to be able to put something in front of you that's three-dimensional enough for you to be able to figure out whether this one's growing or not. They're going to ask the direction of the current using something more stable or static. So they're going to use something like a changing magnetic field or something motional. Does that make sense? All right. This is a sample question that was asked on the exam a couple years ago. I think it's kind of fun. So there were two rails, and at one end, the rails were bent upwards to make an angle theta with the horizontal. Yeah, I know. It's no fun at all. Fun for me, but I saw the look on somebody's face, and they're like, what? Aha. A bar was placed here, and at the other end, there was a light bulb or a resistor of some sort. We'll just say it's got a resistor R. There's a region of space starting at the flat section that has a uniform magnetic field. And we'll say that the bar is L wide. And we can go as far as say this is H. Bar has mass M. And we're going to say that the flat section is sufficiently long to be able to contain the bar and its motion. This is a conservation of energy style question that they've asked a couple times over the years. Let's just take a look at what happens here. The bar is going to have gravitational potential energy because it's above the reference level. Think back to mechanics, correct? And because it has a certain amount of potential energy, if we for the moment say that there's no friction, as the bar slides down the ramp, it's going to acquire kinetic energy at the expense of the gravitational potential energy it has. So when the bar makes it to the flat section, it's going to be clearly moving. And now the bar is sliding this way with velocity v. That part's easy. 1/2 mv squared equals mgh. What happens to the bar when it's here? We have a self-contained loop, and the bar has velocity v. Can you do a little mathematics and convince yourself that the bar is going to experience a force when it's here? We've talked about this a little bit. See if you can recreate. When we talked about taking a whole loop and shoving it into a magnetic field, we talked about where the force would be on that loop. Find the size of the force on this bar as it enters this region of space where there is a magnetic field. You might have to do some fancy right-hand rule stuff on this. And I'll pick on 2 or 3 of you in a minute to help explain this to me. The angle is useless information. There are two pictures of it. This is one of them neat math things. So again, I'm trying to talk to you mathy people who like little math problems. This one's a good one. This one's going to be a first order differential equation. You should like that kind of stuff. But maybe not.